Okay. Hello, good morning. How are you? Next, I will explain detail. I will explain in detail the step-by-step process we need to follow to develop the phase number 4 computer vision, which is the practical component. You already have done something, but in this section, our main goal is to design a simulation which is capable of detecting, tracking, and classifying the direction and movement of multiple objects. To achieve this, we divided the process in something like 7 key stages. The first one is the preparation. The second is data pre-processing. The third is object detection. 4 is tracking. 5 is movement classification. The 6 is results visualization. And the number 7 is report development. Let's begin by the first step. We need obviously to prepare it, the step number 1 is about preparation and environmental setup. We can use Python programming language. We can use as well MATLAB programming language. With different libraries, you can use OpenCV, TensorFlow Hub, NumPy if you are working with Python, or you can use additional tools available in MATLAB. These tools provide a solid foundation for image processing, model implementation, and data manipulation. And this stage, you need to verify all the installations and ensure the video dataset was ready for analysis. The step number 2, the video preprocessing. Obviously, in this step, we import the video file using, in this example, I'm going to use OpenCV and extract each frame. We need to resize the image to 24 by 24 pixels and convert them from BGR to RGB color space to ensure consistent processing. Finally, we normalize the pixel values between 0 and 1. This is a key step which allows us to improve the accuracy of the detection mode. The step number 3 is object detection. For this stage, we employed a pre-trained deep learning model known as faster RCNN inception, ResNet version number 2. This model is available on TensorFlow Hub. The model identifies and classifies objects in each frame, returning bounding boxes, class labels, and confidence scores. This allowed us to locate and label every moving the object in the video automatically, and essential for the foundation for the next step. Step number 4 is tracking, object tracking. One, once the objects were detected, we needed to follow their movement across frames. We could use the CSRT tracker algorithm from OpenCV, which is highly reliable for real-time tracking. After initialization, the tracker with the detected object's position is continuously updated the bounding box as the object moves. This produces a smooth and accurate tracking through the video sequence. We follow with the movement direction classification. In this step, we calculate the horizontal and vertical displacement of each object. If the movement was mainly horizontal, we classify it as left or right. If it was vertical, it was classified as up and down. This simple yet effective logic demonstrates the foundational motion analysis used in more complex systems such as robotics, surveillance, and automatization. The next step is the visualization of results. We will visualize the entire process by drawing colored rectangles around each bracket object and showing the direction label on the screen. We also capture screenshots and recorded short video clips as evidence of detection and tracking. This step will help verify the accuracy of the simulation and detect potential issues like overlapping objects or lighting changes. Finally, step number 7 is the report development. We will need to document the full process in a comprehensive report following the APA 7 edition format. The report includes the introduction, objectives, methodology, implementation details, and final conclusions. Additionally, you will have to attach the Python source code, the video dataset, visual evidence, and the data management and analysis. This ensures that both the technical and academic requirements were fully met. To conclude, this step-by-step methodology will allow you to integrate artificial intelligence, image processing, and programming into a coherent and functional system. Each phase demonstrates the importance of organization, analytical thinking, and engineering rigor in real-world problem solving. Through this practical component, you will transform visual data into knowledge, showing how computer vision can support not only innovation in multiple fields, but also in health, industry, or automatization. Where you can find good videos for the data sets. As a free samples, can use these. This is the data set available by the University of Central Florida. This one is focused on human actions, running, walking, biking. What it is good, it includes clean motion, good for direction detection. The second one is MOT challenge, multiple object tracking. It focuses on people and vehicles in motion under different conditions. What it is good? A benchmark from tracking algorithms, perfect for object motion analysis. You can download the data. It's huge. It's 5.5 gigabytes, but you can use this one as well. It's about 6 gigabytes as well. And the crackle of this one, you can use another author, or another data set as well. This one is good for traffic and urban surveillance. What it is good is a clear multi-object movement, car, pedestrian as well. Obviously, you can use YouTube. And YouTube, you can search specific items like people walking in the street. Some samples of this are this. This is a very good one. Okay. See how people are working. And this video is has it doesn't have licensing. So we have Creative Commons licensing in YouTube filters, like, for example, filters, features, Creative Commons. And obviously you can download the video safely using a YouTube downloader or the PyTube library in Python. It's fine for you. There another one which is cool is this one, Pexels videos. And I look for this one. People walking across. I downloaded this one, which I think is good for the exercise. It's only 30 seconds, but it's fine because you can find pedestrian and cars and cycles, bikes as well. This page or this wish page is recommended for clean, consistent results in the object tracking and direction classification. And this one is ideal. Here we have another one. Yeah, this one. There are multiple moving subjects, the moving directions, left, right, up, down. It's easy to classify. They are short, it's only 20 seconds, and the quality is quite good. So I have prepared the collab solution as well. This is the first one. I'm going to share this one with you, so don't worry, for your reference. But we have what we have here. So we have some kind of references that are included in the reference. This one is one, advanced imaging processing for AI techniques and application. We have this one as well, a data set enhanced through image processing for cultural heritage and machine learning. They use a very nice keywords as a data set. They have defined it like a protocol as well to detection and whatever they need. The next one is a sensor-enabled proximity detection with hybridization for IoT and computer. So we have the camera, we have the input video, and then we have the object detection, the object output for detection. It's good as well. This one is implemented in real life scenario. It's not the more professional, but it's only real-time implementation, which is good. And we have this one as well that comes from the NAT. Redes de sensores inalámbricos, WSNN, is a casual application. Follow as well this literature for you to run your investigation. That's it. So what we have in the Google Colab section. The first one, this is the setup. And obviously here we have the install imports as well the helper. Okay, here we have all the libraries and the imports that we need to do. The second, obviously, we need to include the video that I already told you that I included. It's this one. Sorry, this one. The video file one. The phone to the video. Going to your video. This is the video file. Okay. Number 3 is the CFG. Okay, here we have the configuration. In the configuration, we are going to include the batch size, the thresholds and whatever we need as well. What is down here? Then we need to resize the frames. We need to include the IU, include as well the ID machine. We need to include the direction. Obviously, we need to include some video writer within the solution. So this is the part of the code that we need to use. So please, the size, ID machine, direction. This is part of the function that we need to use. Obviously, I am not going to point-to-point line of code, but we need to revise the code as soon as you have it. We need to include as well the load detector. So we need to include the model. So we are going to use the TensorFlow Hub raster RCNN, which is defined here. This is number 5 vector. This is the TensorFlow Hub servers. Number 6. And somehow this step is kind of optional because you need to have a stable diffusion for small ROEs. We need to have some quality metrics as well, so we need to do that as well. This is number 6. This is the table Rex. That's kind of. This one is used for small ROEs. So we need to add the quality metrics. And number 7. Yes. Okay. Number 7, we need to include there as well the multi-object tracking. With CRs there. We count for OpenCV. And we need to include as well some kind of periodic refresh or periodic detection refresh. Okay, this is the one. This is number 7. This is step by step and I'm using. And this is the main work. Okay, I need to do something before. This is some kind of we need to load properly the hub in order for the system to work. And we need to patch. This is the call the signature. And this is the main loop. So number 2. What does the main loop do? Here we have we need to read the frames. We need to downscale. We need to detect and track. To do the SR. We need to draw. And we need to write in the video. So this is the code that does that. And finally, we need to take or show the output video. Inside the notebook. And we need to some addition, well, some kind of reported super resolution quality metrics. This is done by this indicator, ESNN, divided by the SCP. Obviously, it will take some time to process the code. We are not going to do that in this meeting. You can do it by yourself, but this notebook will demonstrate, obviously, I have assumed the reference included in this scenario. And I have included the robust object detection. I am using TensorFlow Hub faster RCNN model, as suggested in the guide by using strong containment detectors. We have done as well the multi-object tracking via OpenCV, CSRT, and periodic redetection with AOU matching. We have done the direct classification by centroid displacement. We have the left, right, up, down, which is the core requirement of the practice. We have included as well the super resolution for small crops, and we have used the stable diffusion export upscaler with a consistent from a high quality detailed image plus PSNR and SSIM for quality checks, echoing the workflow and metric described in one of the reference, which is done by Johan Faces Super Resolution section. And we have done some scaling of 4K frames to a managed long side, 1280 pixels to balance speed versus fidelity, which is somehow a practical engineering trade-off. Obviously, you can add more functionality in file. For instance, you can include a CSV log of all tracks, frame, ID, debug, direction. You can include a simple confusion like summary to a final direction by ID. Obviously, as well, you can write for block to say outputs to your Google Drive or whatever file you need. Somehow, just play with it. Run your solution with this one if you want, or you can prepare whatever change or whatever version you want. Please don't hesitate in contacting me if you have any kind of questions. For now, this is all for me. I will share this solution with you in the Teams chat. So thank you very much for your attention. Have a good day. Bye-bye.